In this video, I plan to discuss the qualitative relationships within these double replacement reactions where you have a precipitate that forms either double replacement or like a neutralization type of double replacement or whatever. And if you are a little unfamiliar with double replacement reactions, you can go back to the reaction type playlist and take a look at those, and you'll see these rules about solubility and everything else. And when we're looking at the idea of something being aqueous, a literal translation of aqueous, and our abbreviation, by the way, AQ, a literal translation is in water. All right? And for our purposes, we're talking about specifically electrolytes, which dissociate. They separate into ions in solution. Electrolytes dissociate. They separate into ions. So that's the basis for what we're going to do here. What I want us to look at is a simple chemical equation with one-to-one stoichiometry. So we can take a picture of these ions, and by picture I mean draw, some caveman drawing of these ions, and keep track of them through the reaction. So we'll take a situation where we have sodium chloride and silver nitrate. So we'll have sodium with chlorine, and we're going to add to that our silver nitrate, and if you were looking at this, trying to identify the reaction type, you'd say to yourself, hey, I've got two ionic compounds. We're going to have to think of it as probably either the cation switching place or the anion switching place or whatever. In this case, sodium is going to go with the nitrate. And we're going to have the silver with the chlorine. And don't forget, the way we get these chemical formulas is to crisscross and reduce. Silver is a 1 plus, chloride is a 1 minus, sodium is a 1 plus, and nitrate is a 1 minus. All right, we'll pretend that we set that up and completed and balanced it. So we'll just use our table of reactants and products. Stuff happened, it's balanced. Then in terms of double replacement reactions, we had to identify solubility to see what actually happens. We're going to take the complete balanced chemical equation, split it into a complete ionic equation so we can see what actually happens. And then I'm going to draw some pictures of what's going on with the ions specifically. So we need to know phases. In this case, there are specific solubility rules. You can look those up on a table, or you probably know by now. Group 1 metal, probably soluble. Nitrate, probably soluble. Group 1 metal or nitrate, probably soluble. And then chloride, which would be soluble, except we're with silver, so that one's going to be solid, right? That means insoluble, right? And that is precipitating out of solution. And that is going to be a rather important idea for us as we set this up. All right. One of the things that I tell my students is that there's no salt in salt water. It dissociates, it separates into ions for sodium chloride. So that is what we're going to show in this step right here. Our sodium ions, our sodium chloride is going to give us sodium ions, and those are going to be aqueous. Our chloride part of that is going to give us chloride ions. And continuing along there, silver is going to give us silver ions. Our nitrates. And again, these aqueous species are dissociating. They're separating into their ions in solution. There aren't a bunch of NaCl's floating around in a salt solution. There's Na ions, sodium ions, and chloride ions. As we get to the other side there, we're going to have that Na sodium ions and the nitrates. And then this silver chloride, AgCl, that is not dissociating, it's not aqueous. So we're going to end up with, now if we were setting this up as a double replacement problem and looking for a net ionic equation, we would look for spectators and we'd say, okay, spectators are things that aren't involved in the actual reaction. They remain unchanged from reactants to products. Sodium ions going to sodium ions, no change. That's a spectator. Chloride ions become part of a compound. So chloride ions must not be a spectator, something's actually happening with them. Silver ions become part of a compound. That must not be a spectator. It changes. The nitrate ions remain nitrate ions, so that must be a spectator. And off to the side here, I'm just going to sketch out real quickly the net ionic equation, which is going to have those pieces right there, the silver ions and the chloride ions, giving us the solid silver chloride. All right, so that's our net ionic equation. And everything else is just floating around in the solution, and that's something to consider as you look back at double replacement reactions. What I want to do with what we have here is kind of break it up into pictures of what's going on. And I'm going to try and budget my space better. All right, that should be okay. I'm going to draw some beakers here, and it's going to be the beaker with those things in it. That's a beaker. That's also an identical beaker. And that beaker is a little bit bigger. And then I'll fill in the other ones. First of all, what's in these? Well, if they're aqueous solutions, we've got to have water. So there's my water level for each of those beakers. And in this beaker right here, it's aqueous sodium chloride. So I have sodium ions. And I have those chloride ions. And it doesn't really matter where they are in there. They're in there. The silver nitrate, I've got silver ions. And the nitrate ions. And in this side right here, I've got sodium ions and nitrate ions, so I'll just throw those nitrate ions in. And I have the silver ions, sodium ions. And then what else do I have? Well, I have AgCl, which is insoluble. It precipitated out of the solution. It's not actually in the solution. So I've got this precipitate here, and I'll draw it on both sides of that. This is our precipitate, our solid. Right? And it is not in the solution. Right? It precipitated out. So that's kind of important. We have in the beaker sodium ions and nitrate ions. And now let's look, this example right here, we would have stoichiometrically equal amounts. So if you're looking at this, I'm just going to draw a box around these two and say we have stoichiometrically equal amounts. And what that means is we don't have any excess and we don't have any limiting, and so none of these ions are going to be left unreacted in the end and are going to show up over here as a result. So there's no excess. And the other two scenarios I want to look at here are what if there are some excess ions floating around. So this is our next set of beakers. And they're aqueous solutions once again, so we've got our water there. And do take note, like if I had 50 milliliters here and 50 milliliters here, I'd have 100 milliliters total right there. And so that's kind of why I'm skewing the size of these beakers. Starting out, we've still got our sodium ions and our chloride ions. We've still got our silver ions and our nitrate ions. And in the end, we're still going to have this solid silver chloride precipitating out, and I'm still going to have sodium ions and nitrate ions. And then we need to take into consideration what's left. And for this particular example, I'll just declare that this is going to be our excess reactant. And I know that pink is not super easy to see, but that's going to be my excess reactant. This is going to be the limiting reactant. Now, what does that mean? That means I have some of these things that are left over in the end. I have more than I needed. So sodium ions we've already taken into consideration, and qualitatively I'm not worried about writing it again. Chloride ions, though, not all of them are being used up. So I'm going to have some chloride ions over here as well. So this right here, I'm now going to have some chloride ions, right? So from our excess. So in this particular case, I've got my limiting reactant over here. those things get used up, and then I've got my excess reactant over here, and that means I've got some unreacted chlorines floating around in the final solution. And then our last scenario here, just so we've been thorough in our discussion, is if we have excess silver nitrate starting out. One of the things that I always say to my students is step back for a moment and look at the actual reaction taking place in what you have. If you had a reaction like this, and you could choose one of them being present in excess or one of them being the limiting reactant, try to use excess cheap stuff and limiting expensive stuff. And you'd say, okay, well, I know salt, I can buy it at the grocery store and it's cheap. This has silver, that probably costs more. So it wouldn't be unreasonable to just take your silver nitrate solution and dump in a bunch of NaCl. That'd be a situation like the one we had right there. All right, let's get our other ions drawn in. So sodium ions and chloride ions. And I'm going to put those sodium ions over here right away while the red pen is handy. We've got silver ions and our nitrate ions. And I've got my nitrate ions over here. I still have my undissociated species right there. Oops, wrong order. And the way you'd get that solid out of there, a real common way would be using filter paper or something. And now we have to take a closer look right there. In this, we have our limiting reactant. That's all getting used up. And then here we're going to declare I have some excess reactant. So in the end, I've actually got some silver ions that are still floating around in that solution because it's from the excess. And if we can boil all of this down to one key idea, why do we care about any of this? Because we're concerned with what's in the final solution. As we look at solution stoichiometry, we're going to need to know how much stuff is left when we do a reaction. We've done it with like masses, where you say, all right, I've got this mass of excess reactant remaining, and now we're going to have to worry about what's in that final solution. So our key idea here is what is in the final solution. And the first thing that's in our final solution is our aqueous product, whatever we have right here. Also known as spectators. Right? They didn't change from reactants to products, and so they're still floating around in the end there. And then 2, your excess reactant, as long as it is aqueous. So this is our key idea that we're going to carry over into the future videos. The idea that there's 2 key places we're going to be looking for what's present in the final solution, and those 2 key places are your aqueous product and your excess reactant.